Good afternoon, everybody. So today we are going to finish. Make sure I have sound. Yes, I do. Good afternoon. Yes. All right. So today we're going to finish talking about catastrophes in the solar system. And then for the second half of the class, we will get into the next subject, which is the sun, still part of the solar system. Just to remind you that this week you have discussion sections again, and you will be having a quiz once again that is based on your homework number 2. So make sure you study, make sure you get ready for the homework, and hopefully you'll get into a routine from now on. Was there a question? No questions. All right, let me just move that. Okay. All right, so here's the references in your textbook. I'll tell you a little more about that in a minute. But let me just go back to what we were talking about. We were talking about catastrophes that can happen in our solar system due to impacts of comets or asteroids, any of this leftover debris in our solar system. It will, when they hit another planet, another object, another moon, they create a crater. They also can send a lot of debris to the, in our case, to the atmosphere, and it can even cause global extinction. I had shown you several pictures of moons and planets around the solar system that showed a lot of craters. And somebody asked, why is it that all these other bodies in the solar system show all these scars, all these craters, and why is it that the Earth doesn't show so many? So you were anticipating this question, and that's what we're going to talk about right now. Why is it that the moon, why does the moon have so many more craters than Earth? They're right next to each other, right? Why is it? So let me actually launch a poll, and I hope it works. So I'm just going to do one of these generic, choose the best answer. So why does the moon have so many more craters than Earth? And the answers are A, the moon's gravity attracts more asteroids than the Earth's gravity. B, the moon is older, so it has been hit many more times. C is there are many more asteroids near the moon than the Earth. Or D, the Earth has certain features that either mitigate the impacts or erase them after they happen. So why does the moon have so many more craters than Earth? All right. So I'll give you a few more seconds. A, the moon has more gravity. B, the moon is older. It's been around longer to get hit. C, there's just more junk around the moon. Or D, the Earth either stops somehow the impacts, or if they happen, it erases them. So those are the answers. Very good. Everybody finished. And let me share the results. All right. So the answer is correctly, it's D. The Earth has certain features that either mitigate the impacts or erase them after they happen. A few people, a good percentage of people answered A, the moon's gravity attracts more asteroids than the Earth's. That is not correct. In fact, the Earth has more gravity, but that's not as relevant, really. If an asteroid is coming and you happen to be on the way, mostly gravity, what it'll do is it'll change the path of the asteroid. And so the Earth has better ability to do that than the moon. But yeah, that is not correct. Also, C, there are many more asteroids near the moon. That is also not correct. There's asteroids all over, and if anything, there are more asteroids near Mars but Earth and Moon are practically in the same place. So the correct answer is D. Let me stop sharing. The Earth has certain features that either mitigate, meaning that it makes it better, the impacts, or erase them after they happen. So what are those features that help the Earth? Well, the Earth has a very active atmosphere and surface and all sorts of things, right? So the Earth has an atmosphere. There's a lot of air, a lot of gas that is above the surface of the Earth. So for one thing, a lot of the impacts that come toward Earth end up burning up, right? Like the example of Chelyabinsk. Chelyabinsk, the meteorite that came to Chelyabinsk should have caused a big crater. But because we have an atmosphere, it exploded in the atmosphere. It got so hot that it ended up exploding. So that's helpful. The Earth's atmosphere shields us against a lot of the impacts. But once we actually get an impact, then we have other things that will erase this scars, these craters. For example, erosion. We have wind, we have water. And so even though we'll get a crater over time, it'll get eroded and then it's not so easy to see it. We have volcanism, right? We have volcanoes. Right now in Hawaii, the Kilauea volcano is erupting and it's creating this lake of lava. So then it you can imagine how you can have a full surface of full of craters, but then there's a volcano and it erupts all this lava and then it fills in all the craters, so then you can't see it anymore. And then another one, which our planet has and almost no other planet in our solar system has, is plate tectonics. And we have this active surface that is being recycled. And I'm showing here a movie just going from the Precambrian to the Cenozoic. And you probably learned about this plate tectonics, how they move around. And it is like a conveyor belt, right? So some surface comes and then it goes back down, like in this picture, it goes down and it gets recycled. So it may be that part of the Earth gets a bunch of craters and then it goes down, and so then they are all erased. And to give you an example or to show graphically how this works, here is a map of the continents, and it's color coded by how old the surface is. So meaning how old it has been, how much time it has been exposed before it goes under the mantle of the Earth. And you can notice the light yellow is the youngest, and you can see how there are almost no craters. So the red dots are places of impact craters. And you can see how in the yellow, there's hardly any craters. And that's because, this is brand new surface. There hasn't been enough time for it to get craters. Whereas in places that are much older, like more than, in this case, 1 billion years, there's a lot more impact craters. Here's an example. So here's Greenland, which is a lot older, but the problem with Greenland is its ice, right? It's covered, much of it is covered with ice. So again, it's going to be a lot harder to see those impact craters. Let me get to your questions because I see that I have several. Okay, back to the announcements. So how can we find out how we did on the quiz? So you guys may notice that you have 2 different iLearn pages. One is dedicated to this main lecture. That's where I put the homework and the lecture note, the lecture slides and announcements and all that. But you have a second iLearn page, which is dedicated to your discussion section. Your quiz grades will be posted there. So not on the main one, but on your discussion section. And it usually takes the TAs a few days to grade your quizzes. But they will be posting your grade there. And they also give them back to you during your next discussion section. So you'll be able to see your quiz, I think. So you can check with them, you can ask them. Um, um, okay. Are there any other terrestrial planets that have some of the same characteristics that I'm mentioning here? Some of them, for example, Venus has a thick atmosphere, mostly made of carbon dioxide. So that helps Venus. There is, I can't remember, I think it is Venus too, that has some plate tectonics, and there's one of the moons of the Jovian planets that also has plate tectonics. Volcanism, some of the moons of the Jovian planets have volcanism. The most prominent one is Io. So it also has even Mars has a very thin atmosphere, and it has wind and it has sandstorms. So Mars will actually have some of the characteristics that will erase the craters. And if you look at pictures of the different planets, you will see how the craters are a lot more prominent in some of them than others. Obviously, all the Jovian planets have huge atmospheres, right? They're almost all atmosphere. So you also don't see craters in those. Could I go back to the last slide, meaning this one? I hope that's what you mean. Okay, I want to say something that I should say in every class, that whenever I give you things like numbers, like ages, anything like that, I don't mean for you guys to memorize it. This class, I want to minimize the amount of memorization that you do. Mostly, I want you to understand big concepts and to think through things. And you'll see that when we do the first midterm, you will get a feel for what the questions are like. But also in your homework, you've seen that I'm not asking you to memorize, like in a few slides where we'll start talking about the sun, and I'm going to tell you about the radius of the sun, how big it is, how far away it is from here. I don't want you memorizing any of that. I want you to get a feel for the fact that it's very big or the fact that it is very far, but not memorize specific numbers. I want you to think through things, not memorize. All right. I think I answered most of the questions. All right, so we're talking about the moon, right? The moon, why does it have so many more craters? Well, speaking of the moon, where did the moon come from? And if you go to your textbook online on chapter 9.4, it lists 3 main hypotheses and then sort of the leading hypotheses. And the first one is what your textbook calls the fission hypothesis, fission meaning splitting. And so the idea is that the Earth was originally one thing, and then it somehow split into two, a little one and a big one. And so how did it split? They can't figure out how. So then they thought, well, maybe it was spinning so fast that it sort of spun out or spun off the moon. This hypothesis has a lot of problems. Once they were able to use numerical simulations, computer simulations, they put on all the physics that would go into something spinning so fast that it would split. And they realized it's not possible. The Earth would not be able to be spinning so fast and stay as one, right? So that really doesn't work. So to answer your question, Cynthia, no, they were not, right? This is a hypothesis that really doesn't work, but it is one of the main that came, I guess, historically. It's one of the ways in which people try to explain why we had a moon. The second one is what your textbook calls the sister hypothesis. And this hypothesis, what it presumes is that the Earth and the moon form at the same time, more or less in the same way that Jupiter and its satellites, its moons, form simultaneously. So it could be that there were a lot of planetesimals and somehow the moon and the Earth form more or less at the same time. This is one that maybe one of the problems that this hypothesis has is that the composition of the Earth and the composition of the moon are very similar, but different. And if they had formed from more or less the same material at the same time, then you would expect them to be pretty much identical, right? They would have a core, a molten core with iron, and it would have a mantle and more or less the same. But the moon actually is very similar to the mantle of Earth, meaning the outer layers of going to the surface, but it doesn't have an iron core. And it's kind of hard to explain how, if they both form at the same time, how they would end up being different in structure and in composition. It's also hard to imagine like two planets, basically, right? A little planet and a big planet forming at the same time, not interfering with each other. The third one, which the textbook calls capture hypothesis, is simply that the Earth captured the moon, right? They form separate in different places, and then the moon was in an orbit that wasn't round, and so the Earth captured it. This one is difficult, again, because the moon is pretty big, right? It is a good percentage of the mass of Earth. It's about a sixth or so. No, it's sorry, I should have these numbers in my head, but it is a percentage. It's about a tenth or so. So, and I'm sure some of you are Googling it, and you'll let me know. Anyways, the point is, it is a substantial fraction of the mass of Earth. And if something that big were coming toward the Earth, first, it would be kind of hard to trap it. But second, even if it trapped it, it would end up being a pretty elongated orbit. Just in the same way that comets come toward the sun and then the sun traps them, and then they start going around the sun. But they end up in very elongated orbits. This is just because of the mechanics of how it works. So that one is a difficult one. And it would be a pretty big coincidence that the moon would end up having a composition that is very similar to the outer structures of the Earth. So then the fourth one, which ends up being the leading hypothesis, the one that we think is the best, is what is called the giant impact hypothesis. And it is the idea that the moon formed from the debris of a collision between the Earth, as the Earth was forming, and then another protoplanet, so something big enough, maybe the size of Mars, that came toward Earth, and then they collided, and then the moon formed. So this is what I said already. The composition of the moon is very similar to the Earth's mantle, the outer layers of the Earth, but the moon doesn't have the metal core that the Earth has. And how do we know this? Well, we know it from several things. We know the density. We can measure the mass of the moon. We can measure its volume. Therefore, we know the density. We know that it doesn't have a very heavy or dense core in the center. We've sent astronauts to the moon, so we actually have lunar rocks, rocks from the moon, where we can study the composition in gory detail. So we know the moon pretty well, and that's how we know these things. So yes, so the best option is the fourth option. And that's, again, what they call the giant impact hypothesis. So here it is in summary. You have the Earth, and you have something about the size of Mars. So it's a protoplanet. The Earth was originally with its axis of rotation not tilted, just going straight, perpendicular to the direction of motion. This Mars-sized body impacts the Earth. That is, the Earth is still in the process of forming, and then it breaks off a big chunk of the outer layers of the Earth. And that's why the moon ends up having the same composition as the outer layers. So, you know, a couple of hours later, all this debris is off, you know, off in space, basically. And then over time, that debris starts to circle the Earth. And then just like planets form from planetesimals, this little smaller chunks of Earth uh, start circling the Earth, and then they form a moon. So again, this is the rocks that were brought by Apollo astronauts support this hypothesis. And again, this is a hypothesis. It could be refined even more as we gain more evidence, but so far, this seems to be the best option. So let me, I think I have a video just showing in pictures what I just. All right, so so this is just to, you know, the Earth is forming, and then this gigantic thing comes, and it's like it's probably one of the biggest collisions that we had in the solar system. If this proves to be correct, this then it was probably a giant, one of the worst collisions that we had in the solar system. And I got a question during the video that, you know, I really appreciate when you guys ask me all kinds of questions, but especially when I realize something is not super clear. So the question is whether this same thing happened to Jupiter many times, and that's why it has so many moons. So let me just remind you that the moons, and that's why I put this background here to remind you, you know, there's the Jovian planets, which are, the Jovian planets, which are farther away from the sun, and they are much bigger, they're gas rich, and the way in which the moons of the Jovian planets form was like the simultaneous formation, right? Let me go back to that slide. So here. So the way in which the moons of Jupiter happen is, Jupiter, Saturn, Uranus, Neptune, is like number 2 here. The moons form simultaneously. As the planets, the gas planets, were accreting more and more gas, it became like a mini solar system, right? Where the gas going around these big planets form a disk, and within that little disk, all these little moons were formed. So that's how those were formed. And in contrast, if you go to, this, in contrast, so the terrestrial planets that are much smaller, they don't have very many moons. Mercury doesn't have any moons at all. Venus doesn't have any moons. Mars only has 2 little things, and they look like asteroids, and they very much look like they were captured, and they're very small. And it's only Earth that is the oddball, right? Earth is the one that has this big moon. And so that's why they needed to come up with some way to explain it, because it doesn't fit neatly into the solar nebula hypotheses. So that's why we think the best hypothesis is that it was an impact, a major impact that happened while the Earth was still forming. Does the sun have any moons, or are the planets its moons? The planets are essentially the sun's moons, right? We are its satellites. We, the planets, are the things that go around the sun. All right, let me go back to sharing my screen. Here we go. All right, so as I was saying, some things don't fit in that solar nebula hypotheses, right? And you guys have done a pretty good job pointing out some of those things. So one of them, like I just said, the Earth has a large moon. It doesn't really fit in with how the Jovian planets are the ones that get to form these larger moons. Some planets seem to rotate in the opposite direction, right? One of the first characteristics of the solar system that I told you about was that all the planets go in the same direction, they rotate, they circle around the sun, everything goes in the same direction. And this is explained by the fact that everything was formed within a disk. So everything has the same original spin of that disk. But some of them, like here, we have Venus and Uranus. Uranus seems to be rolling on its belly, right? It's not even going like the rest of them. And Venus is entirely going in the opposite direction. So the spin axis seems to be upside down. So what could have caused that? Well, when the Earth was formed, when the moon was formed, if that hypothesis is correct, so I forgot to point out this, when the impactor came and hit the Earth, it tilted the axis, right? So now we end up with an axis of rotation that is tilted by 23 degrees. And this is what gives us the seasons, right? When we are in the northern hemisphere, when the northern hemisphere is pointing toward the sun, we get the sun rays more directly toward us, so then we feel hotter and it's our summer. And when we are pointing away from the sun, then the sun rays come at a at a larger angle, so then we don't get the sunlight as directly, and so then we feel cold and it's the winter. So anyways, that was presumably caused by the impact when the moon was formed. And in the same way, it is possible that Uranus and Venus had tremendous impacts that also tilted their axis to the point where they're not rotating in the same direction as the rest of the planets. And then lastly, another thing that may be explained by collisions, and emphasis on may, we don't really know for sure, but it is possible. The fact that we have water, and some of you pointed this out, here on Earth, the hydrogen compounds were not very abundant right around us, or I mean, they were there, but they were gas. So water was not condensing at the position of Earth when the Earth was forming. How did we end up, and I show you these videos of the planetesimals running into each other, and all you see is like molten lava. And where did this water come from? It's possible that, it is possible that the Earth managed to accrete or accumulate or attract some gas as in its last stages of formation. It's also possible that we got early on in the history of the solar system, we got a bunch of comets, crashing against Earth and depositing all those ices that they have. So water and other hydrogen compounds, maybe they were brought to Earth by impacts with icy planetesimals. So again, this is not, nobody has concluded that this is the right hypothesis, but it is a possibility that a lot of scientists are actually studying and researching and trying to figure out if that is the case. So the interesting thing about this, and as some of you are pointing out in your messages, collisions can cause catastrophes, and they can wipe out dinosaurs, right? And they can cause a lot of trouble. But at the same time, collisions actually may bring, you know, life, right? I mean, they bring, not that the collision itself brought life, but what I mean is the elements from which life could thrive, like water, like the atmosphere, and also, you know, things that are so useful and that we take for granted, such as the seasons on our planet, or the moon, right, which is also useful for like tides and things like that. Those may have been also brought by collisions. So the positive side of the violent universe versus the negative. All right, so that's all I have for collisions in our solar system. And I'm going to move on now to talk about the sun. So I'm wondering if there's any remaining questions. So yeah, there are. How many collisions would it take to bring so much water? Isn't a lot of the Earth covered in water? Yes, so that is one of the problems with this hypothesis. And I don't know the answer to the question, how many collisions, but I would imagine it's a lot. And people work with these models, right? And that's exactly the kind of right questions. Like, okay, how many collisions would you have? How many collisions do you expect that there were? Is there enough time to accumulate as much water as we have? That's exactly how they do. They play this game. And yes, a lot of the Earth is covered in water, but just keep in mind that it's a tiny, 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 it's a tiny layer, right, compared to the size of Earth. So it's just very, very small. Same thing with the atmosphere. We feel like there's so much air and the atmosphere is so big, but compared to the size of the planet, it's very, very little. Could I repeat how the moons of Jupiter are formed? I'm going to encourage you to ask your TAs at this point. They form from gas and planetesimals that were circling around the Jovian planets. But it seems to be something that I'm not explaining clearly, so I'm just going to defer to the TAs or to the textbook. Is there a way to remember the order of the planets? You know, people come with all kinds of mnemonics for this. I think it was like my very educated mother, what is it? Just served us. I forget how it was, but people were upset because the P from Pluto was pizzas, and then there's no pizza anymore. So, but you can come up with your own mnemonic, right? So remember. All right, any other questions about collisions in the solar system? Awesome. All right, so let me now move on to talk about the sun. And let me change my background. Right, so we're going to be talking for the rest of the week about the sun. And again, the goal of this section of the class is to talk about the violent phenomena that happens in the sun and how that affects Earth, right? How is that a hazard to us, or how is it good for us, right? Because it can go both ways. So if you notice, the syllabus is a little bit wrong, and I apologize for that, but it has it's missing a couple of the chapters that are where this material is covered in your textbook. So if you notice, we're sort of jumping around 15.1, 16.3, 16.2, and so on. I will eventually correct it and replace it, but I mean, you have it here in the lecture slides. So just a warning for this particular topic, the textbook goes into a lot more detail than we will cover in class. So don't worry about remembering all the details. Just focus on what we cover in class. So today, for the rest of the class, 12 more minutes, we'll talk about the general properties of the sun and a little bit about the competing forces that happen in the sun. And then for the rest of the week, we'll continue with the other topics. All right, so just a reminder to everyone that the sun is a star, right? Just like the stars that you see at night, it's exactly like those. It is a specific type of star. Later on, we will learn about other types of stars. But ours is a pretty normal star. It doesn't have anything too weird about it. It just happens to be the one that is closest to us. And because it is so much closer to us than the other stars, it looks much bigger. And we can even feel how it is hot. Like we feel the heat. I mean, if you think about it, that's kind of amazing, right? I mean, if you have right now a hot water bottle and I'm standing, like 10 yards from you, I'm not going to feel the heat. So, but the sun is like super far and we feel the heat. I mean, it is close enough that we actually feel the heat. So it is much closer than other stars. But again, just to give you a sense for the magnitude of the distances in our universe, I'll keep talking about how the sun is so close and we're practically in the same place compared to the size of the universe. But so I want to spend a little bit of time telling you how far away it is, right? So on average, the sun is about 93 million miles away from Earth, which sounds like a lot, and it is a lot. By the way, I say on average because the orbit of the Earth around the sun is not perfectly circular. So sometimes we're a little bit closer, sometimes we're a little bit farther away, but on average, 93 million miles. So how far is that, right? I mean, because sometimes when you talk about millions and then billions, like you lose track of how much that is. So let me put it in other terms. Let's say you board an airplane, from a commercial airline, and you travel at the normal speed that an airplane goes, and you head straight toward the sun. How long would it take you to get there? 17 years. Like, like that's crazy, right? When I go visit my family in Mexico, I board an airplane in LAX, and I get to Mexico City in 4 hours. This, like going to the sun, would take me 17 years, not hours, not days, not months, 17 years. And I mean, if you guys think about it, like you're in college, you're probably somewhere between 17 and 25 years old. This is like most of your life that you would have to be on an airplane to get to the sun. So that's crazy. And you're asking me, is that called an astronomical unit? Yes, that is right. All right, so, and this is something Lauren was asking, how long does it take to go to the moon? So to the moon, in a manned spaceship, it took a couple of weeks, right, to get there. So if you were to take that and go to the sun instead, then it would take more than 2 years. So it's still a really long time. And then, we talked about this already, right? Like light travels at a ridiculously fast speed, right? It goes 186,000 miles per second. At the speed of light, it takes 1 second to get to the moon. And even then, it takes 8 minutes and 19 seconds to be precise to make a trip from the sun to Earth or from Earth to the sun. So crazy. It is a crazy, far away place. And yet it's, and yet we can feel the heat, right? Isn't that crazy? I mean, I hope that gives you an idea of how hot the sun is and how much energy it is producing. The other thing is, it is very big. Even though it is so far away from us, it still looks big, right? I mean, this picture behind me, like, it's big. How big is it? Here's a picture, right? This is the surface of the sun, or surface, right? It's a gas, but the visible part of the sun, and it has this sunspots, which we'll learn what they are. And that tiny little speck there, that's the Earth, right? So if you, a close up, here's Jupiter for comparison. Jupiter a lot bigger than the Earth. It still looks pretty small compared to the sun. So the Earth is a lot smaller than the sun. And yes, there are much bigger stars than the sun, but we'll get to that later. So the diameter of the sun is about 109 times the diameter of Earth. That means, like, if you were to stack Earths one on top of the other in this picture, to get from the bottom to the top, it would take 109 Earths to get, just to get the diameter, and let alone the volume, right? And that's actually a question for me to you. So this is also going to be a generic poll. Here we go. So how many Earths do you think we can fit inside the sun? And those of you who like math will be able to do the math. But how many do you think we can fit inside? So we're talking about volume now. And the answers are A, 109, B, 1250, C, 30,000, D, 160,000, or E, 1,300,000. And you guys are getting the right answer. Very good. So how many Earths do you think you can fit inside the sun, right? This is volume. What's the volume of the sun in terms of that of the Earth? All right, let me share the results. The answer is correct. The majority of you chose E, which is 1,300,000 Earths inside the sun. How do you do that in math? You multiply 109 times 109 times 109, you cube it. So that's how you do that. But I'm not asking you to do it. So here we go. So yeah, that is ginormous, right? That is a really, really, really big volume. All right, so here's some other properties of the sun. We talked about the radius already. Here's the number, but here it is compared to Earth. So the radius of the sun is 109 times the radius of Earth. What I want you to remember from here is about how much bigger the sun is than the Earth. That's the part. Why do I want you to remember? One, so that you have a perspective, right? Just how big it is. But this is the kind of thing that someday your kid or your neighbor might ask you, like, hey mom, how big is the sun? Oh, it's 109 times the radius of Earth. No, I mean, it really is kind of a nice thing. So what do I want you to remember? That the radius of the sun is about 100 times the radius of Earth, right? Or that the mass of the sun, this is in terms of how much stuff it has, right? In terms of like kilograms or pounds, is about 300,000 times the radius of Earth. The distance from Earth, no, you don't have to remember that. But, as some of you were asking, 1 astronomical unit, if you can remember like one of the examples that I gave that tells you how far away it is, I think that would be good, but you don't have to memorize that. Composition, I told you already that the solar nebula and the sun and most things in the universe are mostly hydrogen and helium. So this is what I want you to remember, that 98% of the sun is hydrogen and helium. And there's only a tiny bit of the other elements. So 2% of it is heavier elements. Does anybody know who the third, or not who, but what the third most abundant element is in the sun by mass? Not nitrogen, but that's a good, not iron, no. There's very little iron. Not sulfur, nope. Carbon, no, that's a good guess.
Would it happen to be argon?
It's not argon, there is argon, but
what?
No. Not uranium, no. You would have humans like trying to get it from there. Oxygen, that's right, very good. You get the prize. So oxygen happens to be the third one, and it's by mass, it's 0.8% of the mass of the sun. So it's very little, but it is significant, right? And not vibranium. Right, it's not Wakanda, no. All right, so yeah, that's what I want you to remember, mostly hydrogen and helium. Next class, we're going to learn about how hydrogen is becoming helium. So hydrogen will go down, helium will go up, and the heavier elements are only about 2%. And the power output, so this is how much light it puts out. I don't want you to remember that at all, but it's just such a huge number, 3.8 times 10 to the 26. In English, in words, that's 3.8 septillion watts. And just compare it to your 100-watt light bulb that you have at home. It is ridiculous, right? It is 3, 8, and 25 zeros. So very crazy. All right, so how does the sun work? And yeah, it's 4:50, so I'm gonna have to stop there. Before you go, somebody asked, are we having a midterm? So please look at the syllabus. That's where it tells you when the 2 midterms are. The first one, October 25th, it'll be during class. So absolutely everyone has to be present during that hour, not on Zoom, but it'll be online. So mark your calendars. You cannot miss class that day. And I'll give you a lot more information about it. So stay behind if you want to ask questions, and otherwise I'll stop recording and I'll see you on Wednesday.